Hi friends, in the last lecture we have seen the change of scale property that if Laplace transform of capital Ft is equal to small fs, then Laplace transform of f of at, we are changing this t by at, then this becomes Laplace transform of this becomes 1 by a small f of s by a. So this we have proved in the last class. Today we see an example or application of this problem, and maybe start with this example. Uh, Suppose you have given that ft equal to t to the power n. Now you have to find what is the Laplace transform of f of at. So what is f of at? Then f of at will be a to the power n, t to the power n. So we want to try to find what this would be. So by the change of scale property, Laplace transform of f of at is equal to 1 by a L of f of s by a. So this is equal to 1 by a n factorial s by a to the power n plus 1. So if you see here, so this was our formula. So if you just put here 1 by a and Laplace transform s by a. So what is the Laplace transform of t to the power n? So you know that Laplace transform of t to the power n, where n is an integer, this is given by n factorial by t to the power n plus 1. So whenever you are given s by a Laplace, so what would it be? So if you putting, sorry, here this would be s. So if you put s by a, then it becomes n factorial by s by a whole to the power n factorial n plus 1. So I am writing this thing. I just written this line. And now you just simple calculation. You just calculate and see that you are getting this formula a to the power n factorial s to the power n plus 1. Similarly, you can try and prove this following exercise. These are very basic, easy example exercise. So you can try for f t equal to sine hyperbolic t, f t equal to cos hyperbolic t, f t equal to sine t, maybe for e to the power t, and you know all the formula and the result. What is the Laplace of e to the power 2t? You know that. So if you find for e to the power t and then try to find it what is the e to the power 2t and 3t using this formula. Next we discuss Laplace transform of derivatives. So this is very important formula and very useful too. So if Laplace transform of capital F t is Fs, that is its notation, then Laplace transform of f dash t. So Laplace transform of f dash t is given by s into Fs. This Fs means s into Laplace transform of Fs Ft, capital Ft, and then minus f0. So this f0. So this is the formula for Laplace transform of derivatives. How can we prove? Laplace transform f dash t equal to, we just write the definition, 0 to infinity e to the power minus st f dash t dt. Then this is equal to, again we use the property of the improper integral. This is equal to limit p tends to infinity, 0 to p e to the power minus st f dash t dt. Now use here the rule of integration by parts. So integration by parts, integration by parts. So use that formula. So what would you get? You keep the first function as e to the minus st is the first function, e to the f dash t is your second function. So first function is fixed, so e to the minus t st is fixed. Now integrate this f dash t. So what would you get? Integration of f dash t becomes a simple ft, because integration and derivative are the inverse to each other, and the limit will be 0 to p. Next, you keep this. You need to, in the second time, you need to differentiate this first function. So if you differentiate, so e to the minus st gives you e to the minus st into s, and it into minus s. This minus s comes out, and this minus minus plus. So this thing's happening, and again, if you integrate this f dash t, then you will get ft dt. This is simple application of the inverse by parts. So now put the value. If you put t equal to p, then you get e to the minus sp fp. If you put t equal to 0, then f0, and e to the power 0 is 1. So you are getting minus f0. Plus in the second time, we are getting s0 to p e to the power minus sp ft dt. Again, what is this? This s is as usual, and this is the Laplace transform of ft. So we are at ss fs. So this is simply Laplace transform of ft. This is equal to Laplace transform of ft. So this term is again, if p tends to 0, this term is 0. This term becomes 0. And f0 is as it is an sfs. So we get formula sfs minus f0. So this is the important formula you may remember. For MSc student, you need to understand this proof. And for BTech student, I don't think this is understanding the proof so much important, but you need to try to solve many problems or exercises. Similarly, if it is given that L of f double dash, what is the formula for that? This will be a square fs minus sf0 minus f dash 0. And in general, for arbitrary nth order derivative, you are getting Sn Fs minus s to the power n minus 1, capital F0, s to the power n minus 2, f dash 0, minus f to the power n minus 1, 0. Now we try to solve some example. Try to find the Laplace transform L of 1. You already know that this is L of 1 equal to 1 by s, but we try to solve this using this derivative formula. So we know that this is the derivative formula, a Laplace transform of f dash t equal to s L of ft minus f0. So what is choose your ft as 1. So because we want to find the Laplace transform of 1. So choose ft equal to 1, then f dash t equal to 0 and f0 equal to 1. Because this is a constant function, so every t you will get 0, so f0 equal to 1. And if you differentiate this, then we'll get differentiation of 1 is 0, so f dash 0. So put the value. So Laplace transform f dash t is equal to 0, so we put f dash t equal to 0, and then s of L, f t equal to 1, we put 1, and f0 is again 1. Now you have L1 equal to just L0 equal to 0, and s of L1 minus 1, and simplifying this, you get L1 equal to 1 by s. So these are simple applications. Similarly, you can try to find the similar way, L of t equal to 1 by a square. Uh, I just solved it here. This is very simple. You can try yourself, and if you stuck anywhere, then you can see the formula, pause the video, and see the how I have done. This is the detailed solution is there. You can check. Similarly, for Laplace transform e to the power at equal to 1 by s minus a. You all know these formulas already from the basic definition, but using the differentiation formula, you also can solve this. So again, you pause this video and see the solution, or you can try your yourself, and if you stuck anywhere, then you can see the solution. And this is for similarly for sine 80. Here is a catch for sine 80. We uh, first suppose f t equal to sine t, then when differentiating twice, so you use the formula of twice differentiable formula, which is this cross differentiable formula, and put this all values, and you can get the result. Similarly, you can do it for Laplace transform of cos hyperbolic using derivative formula, Laplace transform of this t sine bt using derivative formula. So try these problems. Now we try, after the derivative, we will try to solve the integration. So Laplace transform for integrals, let ft, capital Ft be a real function such that it needs to assume some property such that ft is piecewise continuous on every finite interval in the range t greater than equal to 0. And there exists constant k and m such that mod of ft is less equals to m into e to the power kt for t greater than 0. So we need these two conditions. Then Laplace transform for this integral will be exist, and it is given by the formula Laplace transform 0 to t ft dt 1 by s L of ft. So this is the working rule or formula. You need to remember this formula mainly for BTech students. And now I'm going to prove. Proof are not, I think proof are not so much required for uh, engineering background student. They need the formula for that. But if anyone interested, they can see the formulas. The formula is mainly intended to for the chemistry students. So if k is negative, then minus k is positive. So suppose if k is negative, then we take k as a minus k is also positive. In that case, we can write mod of ft is less equals to m e to the power kt. So this is given in the condition. If you see the condition, so I need this condition. If mod of ft is less equals to m of e to the power kt. So k can be any constant, positive or negative, but if it is negative, then we can convert it to a positive by the following argument, that if k is negative, if k is positive, then it is okay. But if k is negative, then we can write this as m by e to the minus kt. So now here this minus is positive number. So m and this is a positive number. So e to the power minus kt is always greater than 1. So you divide this something. So I can say that this is less equals to m e to the power minus kt. So we can always assume that k is a positive number. So there is no harm on it. Because if k is a negative, we can find k is a negative number, we just take the negative of that negative number. If k is minus 2, in the negative of minus 2 is the plus 2. So there's some k exist always. Now we try to find the Laplace transform of this integral formula. So suppose this is equal to some capital G. Therefore, GT is continuous. So this is the result from integration, that if you take any function which is piecewise continuous even, but this integration will be always continuous. So I may write here, if ft is piecewise continuous, then gt is continuous always. So this is not only true for piecewise continuous, but if for any function for which integration is exist, this is a result from Riemann integration. So we don't go to that direction, but we just use the result that if ft is any function for which Riemann integration is exist, we can integrate that. The integrating function will be always continuous. So if gt is continuous, now mod of gt, you can write this is equal to mod of integration 0 to t ft dt, which is less than 0 to t mod of small ft dt. This should not be small. This will be capital. There will be mistake. This will be capital. We just take the inside. This mod will be inside. We take this mod inside, and this will be greater equal to. Now put the value. Put the value of ft. What is your ft was always, we assume that your mod ft. We assume that this is equal to e to the power kt. So we put this value here. Now your m comes out because m is a constant positive number, and this is mod of e to the power kt is exactly equal to e to the power qt for positive t. And if you take the integration of that, so you will get this is equal to m e to the power kt minus 1 by k, and we make it much bigger, so we eliminate this value. So this is more bigger because this is a negative number. M is a positive number, k is a positive number. So minus 1, this is a negative number. So we make it bigger and we will get this value. So your mod of gt is always less than m by k to the power kt. So this gt is always bounded. So g dash t is, if g dash t is equal to ft, and if what what have been taken as the property of ft, first property, that it is equal to except for point at which ft is discontinuous. So with this, and so therefore g dash is piecewise continuous on every interval, and therefore the Laplace transform will exist. Laplace transform will always exist for the piecewise continuous. Therefore Laplace transform g dash t is exist, and now we use the again derivative formula. We use the derivative formula. So L of g dash will be s into Laplace transform of g minus g0. So what is g0? So g0 means 0 to 0. Here for gt, here you have a t, or small t, you have a t here, like this. So g0 will be 0 to 0 ft dt, and that is 0. And therefore we get L of g dash equal to slg, which implies lg equal to 1 by s L of g dash. And what is g dash here? So g dash again, you are just taking the function, original function. So therefore Laplace transform of 0 to 2, I just put the value of g. This is your g, and g dash will be your simply f. So this is 1 by s L of f, because derivative and integration are inverse to each other. So g dash is equal to actually f. So we put this value and we get the result. Now we can try to see an example. Find Laplace transform of t square using L1 equal to 1 by s. So suppose ft equal to 1. Then Laplace transform of f equal to Laplace transform of 1, and you already know that this is given to you 1 by s. Therefore, Laplace transform 0 to t ft dt is equal to 1 by s fs. By the integration formula, we already proved that above. You can see the formula again. Now, what is fs? Fs is the value of fs is 1 by s. It is given. So this is equal to 1 by s square. So now put the value here. What is our ft? We have taken ft as 1. So put 1 here. So integration 1 dt will be t. So Laplace transform of t equal to 1 by s. So from 1 you come to t, and repeat the process for t again. Now you choose gt and repeat the same process. Uh, Repeat the same process and you can obtain this result. So using integration also you can find these different formulas, and few exercises. Laplace transform also, using Laplace transform you can find the sine bt, cos bt, and using L1 you also find this cos bt. This problem is very interesting. You can try this. So that's all for today, and in the next class we'll try to find the inverse Laplace transform, because I already told that the Laplace transform mainly used to solve complicated differential equations. So and you transform those differential equations to small, easier differential equation by Laplace transform. You solve there, and you need to come back again your original space. So for that, you need the inverse function also, inverse Laplace transform. In the next lecture, we will see the inverse Laplace function.